Okay. Welcome everyone. My name is Louise Willingale and I'm the Associate Director for ZEUS, and I'm going to be presenting this town hall today. We'll talk about the facility status and the 2027 call for proposals. I will have plenty of time, I hope, at the end of this meeting so that you can ask your questions. And feel free to chime in if you've got questions along the way. Franco can help me out if people have asked them in the chat. Okay, and I apologize in advance if you've been to one of these before. You may see some of the similar material, but I hope there's information that you can use for preparation of your proposals. All right, without further ado, so this is the first of two town halls. We're going to have another one in December, so tell your friends if they have missed this one. All right, so today what we're going to go through is an overview of the laser system, an overview of the target areas and the science that we typically do in the target areas. And then I'll talk about the ZEUS commissioning and status, the capabilities we hope to have for FY27. Then I'll talk about accessing the facility and how you would go about making your proposal and the proposal process. So just to introduce the ZEUS team first. So I'm the Associate Director. Carl Kruschelnick is the Director of the facility. We have a number of co-PIs who also participate in the science direction. We then have the people who you might interact with. Yong Ma is the experimental manager. Bixu is the laser manager for the facility. And then we have a number of link scientists, Anatoly and Paul, and Milosh, who work to connect with the users and integrate their experiments onto the facility. We then have lots of other people who you might meet along the way, including a data scientist, our engineers in the more experimental side of the facility, and then our laser engineers and scientists who run the laser. We also have some target fabrication capabilities on site, and our administration and outreach folks as well. I'd like to give a little shout out to our external advisory board who help give us advice and keep ZEUS running as a facility for you all. Okay, so ZEUS is actually an acronym standing for Zettawatt Equivalent Ultra Short Pulse Laser System. And so the acronym is actually alluding to the trick that we can play if we had a zettawatt power pulse, which is several orders of magnitude greater than our 3 petawatts, then you could reach critical field strengths in the laser focus that would exceed where vacuum could be broken down and spontaneously create electron-positron pairs. So in order to get the equivalence, we have to play a trick, and that trick is to counter-propagate a high-energy electron beam with a high-intensity laser pulse. And so in the rest frame of reference of these electrons, they will see an equivalent field to a zettawatt power pulse. And that should initiate interesting QED effects that will influence the plasma physics that you might observe. So that's kind of the cartoon of the signature experiment that can be performed with the facility. However, there's many more types of science that we can cover as well. As a very broad overview to the facility, here is a floor plan. You can see we have a large clean room which houses the laser itself. I'll go through that in a moment. And we have 1, 2, 3 target areas which the users can access. Additionally, we have a control room where users can sit, target preparation facilities, and the laser control room is over here. So that's just to orientate yourselves in the facility. And here are a few pictures, and I'll go through each of these individually in a moment. So starting with the laser, It all begins with the front end. This is supplied by Amplitude Technologies. We start with the oscillator. It's actually a double CPA system, so it begins by stretching, amplifying, down selecting the pulses, adjusting the spectrum, sending through another amplifier, recompressing so that it can go through an XPW module, which helps us to control the intensity contrast of the final compressed pulse. We then restretch, reshape the spectrum, go through a ring cavity, down select again, more amplification before it goes through a 5-pass amplifier. And then we have 1, 2, 3 main amplifiers in the system, which get progressively larger crystals. And if this is all goes very well, we can get 120 joules out of this amplifier chain, and it can run with a shot rate of a shot per minute. We can then send the light to one of 2 compressors. We have a large compressor which can take the full 120 joules and compress to 25 femtosecond pulses to give us the 3 petawatts, or part of the pulse can go to a smaller compressor which can get output 12.5 joules, taking 12.5 joules to target in 25 femtoseconds to give us half petawatt pulses. That's the general scheme of the laser. So we can have we can actually split the light and send part to the big compressor and part to the small compressor to get joule pulses in target area 1, which I'll explain later. So here on the floor plan, I'll just show you where things are placed. It begins over in the corner here with the amplitude front end, supplying the oscillator pulses and amplifying them initially. We then send them through the 1, 2, 3 amplifying stages to get to the high energy. The light then gets sent to either the large compressor or can be split off and taken to the small compressor here before the light then gets distributed to the various target areas. So in terms of the laser, I've got a list here of the diagnostics that can be run for the laser. And so on shot, we can measure the laser energy, the beam profile, both before and after the compressor. We look at the laser spectrum, and we have a leak through taking a far field measurement so we can get an idea of the laser focus. Off-shot measurements that can be made include pulse duration using autocorrelation or frog measurements. We can look at the laser spectrum and the focus and wavefront in target area 3. So each beam path has 2 deformable mirrors per beam, one that's in air before the compressor and one after the compressor that is in vacuum. So to give you the updates on the laser, a few months ago, it was successfully 90 joules of laser energy was successfully amplified, and so the throughput through the compressor was over 50 joules. When you combine that with the 25 femtosecond duration of the pulse, this took the power of ZEUS up to 2.1 petawatts. So we've exceeded 2 petawatts at this point, and I'll show you some experimental results in a moment that were done with those 2 petawatt pulses. But in addition to that, I just wanted to give you the update towards 3 petawatt pulses. It has been demonstrated that 120 joules of light can be amplified, which if it went through the compressor would give 70 joules on target. So you can see the beam burn here. So the thing that's limiting us at the moment is the imperfections in the beam. We're concerned that this would be above the damage threshold for our gratings. So the laser team is currently working on improving the uniformity, the spatial uniformity of the beam so that we can send it through the compressor and start doing experiments with the 3 petawatts. So we are making progress, but we are not quite there yet. So once the laser pulse has been compressed, it can then be sent to one of 3 target areas. So I'll go through each of those in turn. First, we have target area 1, which is where we have currently the largest vacuum chamber with the large aperture optics. So this can take the full 3 petawatt pulses in this area. The light comes from the compressor. It comes off a deformable mirror in vacuum and then gets sent to a very long focal length optic, which actually sits in the laser clean room in a vacuum chamber over here. It then comes to focus. Typically in this area, we use gas targets, although it doesn't have to be to do wake field acceleration. We also have the ability to take the light from the small compressor and send it into target area 1. Again, we have another deformable mirror, and if you're doing the split beam option, that light can then be taken to a short focal length for a colliding beam geometry, and we have done the first colliding beam experiments at this point now. So just these are now outdated photos before a lot of extra things were put into the areas, but you can see the target chamber here going into the beam dump. This is a large amount of shielding around the beam dump. The beam dump's down here, and then that's the other side of the radiation shielding that you can see. So that's inside target area 1. And so the possible configurations that we're hoping to offer in FY27 are having the long focal length for the single 2 petawatt beam, or having a split beam configuration with 1.5 petawatts for a laser wake field interaction, and then the 500 terawatt beam getting focused with an F3 parabola. And I noticed just before we started that that isn't the configuration I'm showing in the picture, so I apologize, but it will be an F3 parabola with a 75-degree off-axis angle, but the cartoon is similar. In target area 1, we have several semi-permanent diagnostics, which include a triple magnet electron spectrometer. Typically, we've been using the first 2 magnets, and the third one is pushed out of the way at the moment, but it has the ability to measure up to greater than 10 GeV electron beams. And there's also the option to use an optical probe beam as well to look at the interaction. The science in this area is largely focused around laser wake field acceleration of electron beams, although there is another group that's doing something different right now. But laser wake field acceleration is one of the primary how it's been designed for. So if you put in a gas target, you can accelerate your electrons, and then the colliding beam experiment has been designed so that you can be pretty flexible, and it's building up to the study of the QED effects in the experiment. I wanted to show a few results from some internal experiments using the 2 petawatt beam for electron acceleration. So these were shots taken earlier this year over a few days, 51 shots taken over 3 days. They used gas cell targets filled with a helium-nitrogen mixture, and you can see some interferometry that was done on the experiment. Using the 2 petawatt pulses, you can see some of the experimental data here. So we have this is a double magnet spectrometer, and we have 2 screens, scintillator screens, which record the electron beam. On the left-hand side, you see the low energy part of the screen, and on the right-hand side, you see the high energy part of the screen. So with the 2 petawatt pulses, we were getting electron beams exceeding 2 GeV, but in fact, we saw multiple beams forming, likely due to an asymmetric focal spot. And therefore, it's believed that guiding will be necessary to achieve higher energies at higher electron energies at 2 petawatts. Having said that, pretty nice electron beams can be generated using the 0.5 petawatt pulses. So it's already been demonstrated that 2 GeV electron beams can be produced. So this is data showing that as you increase the gas cell length, you can increase the energy of the electron beam. In addition to the electron beams, this has been published in Paul Campbell's recent paper in POP. This is data taken from several shots at the same conditions. The average charge was around 18 picocoulomb, if you exclude this weird shot 4 here, which was an outlier. In addition to the magnetic spectrometer, we also have an electron beam profiler. There's some streaking due to fringe fields, and we can make X-ray betatron measurements using an X-ray CCD and filter wheel. Moving on to target area 2. Currently, we are restricted in this area to the taking the half petawatt beam line due to the chamber size. Now, the important thing for target area 2 is that we are expecting to upgrade the size of the chamber and the size of the optics during FY27. The exact timing for this is a little bit undetermined right now due to the fact we want to minimize downtime, and it will depend on the lead times for all of the items coming into the area. However, we hope that we'll be able to offer some time with this smaller chamber setup. In this area, it's designed for short focal length configurations, and we have double plasma mirror and deformable mirror options as well. So the light comes in, it's focused down and goes off a double plasma mirror before being recollimated to be sent into the chamber. You can bypass this double plasma mirror option and send the light straight through. We then use a short focal length optic to get to high intensities, hopefully with high contrast. So a few commissioning results from this area. So the commissioned diagnostics are off-shot laser focus and wavefront measurements, on-shot laser far-field and near-field measurements. We have a Thomson parabola ion spectrometer that can be used, and the results from that, the MCP data is shown up here. We can see the up to 7 MeV protons were measured. There's a pin diode for soft X-ray detection, photomultiplier tubes for gamma ray detection. We have image plates and scintillating screens for a variety of measurements. The idea here is to reach the highest intensities with high contrast, which could be used for thin, solid target interactions, for gamma ray generation, or for high harmonic experiments, or whatever you imagine as well. And then finally, the third target area 3. This was the existing Hercules target area. It has a chamber that has been primarily designed for laser wake field acceleration of electrons. There are 2 off-axis parabolas, the F20 and the F40 that can sit out here. We have a pick-off to take an optical probe, to create an optical probe beam. It can run at 200 terawatts at a 1 Hertz burst operation mode, or at the high power of 500 terawatts at 1 shot per minute. So you have some flexibility there. There are a number of semi-permanent diagnostics, including laser focal spot measurements, wavefront measurements, laser pointing. There's a magnetic electron spectrometer, which is shown over here in the schematic. There's an electron beam profiler, X-ray CCD diagnostics, and an optical probe beam, which can perform interferometry or shadography. Typically, we use gas targets in here, which is somewhere down here. As I mentioned, primarily this is for laser wake field acceleration of electrons and the high energy photon beam generation, but the intention is that these could be used for probing applications, including for non-traditional high power laser users, perhaps material scientists, or people who are interested in biological imaging and that kind of thing. They could come here and do some experiments as well. We do have a suite of diagnostics available. There is a link on the ZEUS website to a Google sheet which lists some of our diagnostics. We're happy to try and provide more information about any of the diagnostics that you might have questions about, so please contact us if you would like to know. But we have a pretty broad range of instruments available, and we have plans to acquire more as well. If you wish to bring your own diagnostics onto the system, that's also possible. During the planning process for an experiment, that would require assistance from our mechanical and electrical engineering staff to make sure your diagnostic can be integrated and the operation is safe for the system. On site, we have some target fabrication capabilities. We partner with Sally Klein's group, Carolyn Carran's and Sally Klein's group, who have a great set of facilities that they can use to create filters and targets. We also have the ability to 3D print, and we use this regularly for creating gas cells of different designs and varieties. We can shoot flat foils. We're preparing liquid jet targets. This has been trialed. It is tricky, let's say, but that is also possible. And then if you require some very fancy specialist targets, it may be possible. However, we'd have to do a cost analysis, an assessment if ZEUS can provide those, because these can end up being extremely expensive. So in terms of the capabilities for this call for proposals, it looks pretty similar to what we're hoping to offer in this coming year. We're hoping to run at 2 petawatts in target area 1 with the aim to reach the 3 petawatt capability, providing the beam properties can be successfully modified. We'll be offering the split beam option in target area 1. There are no plasma mirrors in target area 1 to clean the contrast, but we have depending on your configuration, we have the long focal length, we have a long focal length, short focal length configuration, or the opposite way round with the low power for the long focusing and the high power for the short focusing. Target area 2, we're aiming for improving to get to 500 terawatts, but we are confident with the 200 terawatts available. It runs at a shot per minute. It doesn't currently have a split beam option, but we're planning one for the upgraded area. There is a double plasma mirror. So the power after the double plasma mirror, for 200 terawatts on the plasma mirror, you'd get about 125 terawatts after. It has F2 focusing. F2 focusing, and we'll be, I don't think I mentioned in target area 1, we'll be able to offer the long pulse, which I will tell you about on the next slide. Target area 3, we're aiming to run at 500 terawatts. The plan is you can have the 200 terawatts in 1 Hertz burst mode, or the 500 terawatts at a shot per minute. The eventual aim is to bring this burst mode to 5 Hertz at 500 terawatts, but we're not there yet. There's no split beam option or plasma mirror option in target area 3. There are the 2 different off-axis parabolas, and we're hoping to put the long pulse through into the target area 3 for this coming call for proposals as well. So I mentioned the long pulse capability. We have in-house and commissioned an amplitude intrepid laser. So this is a commercial system. It's set up to run at the 2nd harmonic. And so at 1 shot per minute, it can output 75 joules in 10 nanoseconds, or 35 joules in 1.5 nanoseconds. So the idea behind having this is that we'll be able to perform pump probe experiments. So an example here is a shot front being generated by the long pulse driver and then being imaged by the short pulse X-rays that were generated. All right, changing gears a little bit from the laser capabilities, I wanted to mention something about the users. So hopefully some of you are interested to be ZEUS users. We've now, we're in our third year of experimental operations now. So our first year we had 24 weeks of external user time. The year we've just finished had 30 weeks of external user time, and we're entering 2026, which will have another 30 weeks of user time. So 30 weeks is our full capacity. We've had 15 external user campaigns with over 93 users. 61 of those users came to made on-site visits, and 49 of those visitors were students or postdocs. So there's a full list of the experiments available on the ZEUS web pages. There's quite a lot at this point, so I thought I wouldn't go through them all. But last year, just to give you an idea, the call for proposals from last year gave us 17 proposals, and 8 of those have been scheduled for FY26. We've got a large variety of institutions where our users came from as well. So that's just what this plot is showing at the bottom here. The feedback from external users is extremely important to ZEUS to try and improve our operations as a facility. And so I wanted to just show you a summary of the feedback that we've had from our questionnaire so far. Overall, it seems that the laboratory is performing very well, and people would recommend ZEUS as a facility for performing your experiment. It seems we have good communications with the teams. We have good safety and spaces for the users. The administration also seems to be pretty good. The places where we have some issues are with data acquisition. So if you're running at one of those high shot rate experiments, it was found that the data speeds were not currently sufficient. So we are working on upgrading the network to ZEUS to accommodate these higher data speeds. And the other place where we have some feedback that is not so good is that housing can be pretty expensive in Ann Arbor. This is exacerbated in the fall season because we have football, which makes the housing prices go up. What I will say is that ZEUS will work with users on solutions to this if you are having difficulties here. So coming to the call for proposals, we have an annual call for proposals. This new one is now open. When you send in your proposals, we send them to an independent review panel. That means no members from ZEUS, the ZEUS facility or QoS are there to assess them, assess the science and rank them based on the science. We do look at the feasibility of doing the experiment on the facility. So access gets granted for fundamental research in physics, medicine, engineering. That means that we're not doing industrial or commercial experiments. It has to be publishable research. And also no classified research can be conducted on ZEUS either. So the proposals are ranked based on the best science. So it's really important to write that into your proposal about why the science is very critical and the impact of that science. So then the ranking of the proposals gets passed to the ZEUS facility for checking for feasibility and then for scheduling. So each experiment gets assigned a local scientist, our link scientists, and that helps initiate the planning. We connect the users with the ZEUS user office to arrange the training before their arrival. And we also, as I just showed, we expect users to provide us with constructive feedback so we can make any improvements in the future based on users' needs. This is a kind of cartoon, but typically planning for an experiment starts at least 3 months ahead of the scheduled time, and then a minimum of 3 meetings would happen before users would come on site. These meetings would include the target area link scientist, the PI and user team, our local engineers, and a laser representative. So we aim for at least these 3 coordination meetings so that we can finalize the experimental designs. It's really important for all users to use the My ZEUS portal. It's sort of our one-stop shop for all things ZEUS related, where you submit your proposal, you plan your experiment, you collect your data afterwards, and you communicate with the facility. So check out My ZEUS portal. Again, as a sort of overview of how we run things at the facility, we have 2 shifts of laser staff. So early in the morning, the first shift will arrive to warm things up and start the alignment and maintenance for the facility. Users arrive maybe not at 8 a.m., but perhaps at 9 a.m. to have a morning meeting with the local scientists and staff. The laser is typically available mid-morning for first alignment and then high power shots. The second shift arrives around lunchtime and then run the facility through into the evening when we close down. Oh, it may be possible for you to come and have access to the target area before your access to the laser begins, and that will allow some setup to take place as well. So our 4th annual call for proposals is open. The announcement went out to the user group email list and is on the ZEUS website. We're having the town hall now, and we'll continue advertising this in various ways over the next couple of months. Proposals are due mid-February at 5 p.m. Eastern, so February 16th at 5 p.m. Eastern time. The expected capabilities were on that chart that I showed, but they're also posted on our website, and feel free to contact us if you have any questions about those. We'll be aiming to schedule 30 weeks of external user time. Typical experiments might be 3 or 4 weeks long. Certainly shorter is possible. Longer needs significant justification. In terms of eligibility, we welcome proposals from the whole scientific community, from both within the plasma physics community and beyond. There's no restrictions on your funding support, but if you have any questions, let us know. International researchers are also welcome. We're really looking for the best science that can be done on the facility. So I mentioned My ZEUS portal as the one-stop shop for users. This is our web-based interface with the facility. So here you'll see you can access it if you go to the ZEUS webpage, and then under the tab on users, you'll find the My ZEUS portal. So once you've registered, you'll have access to more things. You can see without even registering, you'll be able to look at the calendar for the facility and what's planned for the facility and the laser status. Once you register, you'll be able to give information about yourself. You'll be able to upload proposals and see how the status of your proposal, as well as if your proposal gets allocated experimental time, then you can start setting up your experiment here. So it was a portal that was developed in-house. It seems to be up and running pretty well, but please let us know if you encounter any bugs along the way. And then once you've done your experiment, your data is also available through this webpage. So in terms of how to submit your proposal, first thing to do is to register for a user account, then prepare your proposal according to the requested proposal preparation guidelines. These are available on the ZEUS website. There's a form then to fill out on the My ZEUS portal, which talks you through this. If you have any questions along the way, please contact myself or the email address shown here. Any questions you might have.
What's the problem?
Is there some feedback? Somebody's got their mic on. I hear some feedback. There we go. We're going to have set up, and we'll advertise in due course, some Q&A sessions. These will likely be in early next year so that you could speak directly with the ZEUS team. You're also welcome to email us at any time that you would, and we'll try and get back to you as soon as we can. And then the important thing is to get your proposal in through the My ZEUS portal before February the 16th at 5 p.m. Eastern. And before I finish, I wanted to advertise that we are planning a multi-petawatt diagnostics workshop. It's planned to take place at the University of Michigan on the 21st to 22nd of May next year. For those of you who might be NSF funded people, you may already be planning to come to the Eclipse meeting. The Eclipse meeting will happen in the 3 days before this diagnostics workshop. You don't have to come to Eclipse, you are welcome to come anyway. But the goals of the workshop will be to understand and identify diagnostic technologies that will be used to address scientific frontiers for multi-petawatt facilities, including ZEUS. So we're partnering with the Opal team to prepare this workshop. We're looking to identify technical gaps in bridging present diagnostic solutions to the multi-petawatt scale and leveraging technology solutions from complementary fields. For example, we're thinking of the accelerator community. And then we want to sort of develop this idea that we can connect people across our various communities to bring our diagnostics up to where we need them to be to do these really hard experiments. At the moment, we're working on 3 main target areas, one on hard X-rays, one on particle beam diagnostics, and another on ultra-fast, high-power optical diagnostics. That might be before or after the interaction. So please get in contact with us if you're interested in participating in that. There will be more information coming out shortly, and a call for white papers as well. So just to finish on the ZEUS Town Hall, we have up to 3 petawatt power laser to perform experiments on testing extreme field physics, to create unique particle and photon sources, and to use these sources for various types of STEM experiment. We are a user-based facility. That doesn't make any sense what I just said. We're a facility who provide user access through a scientific merit-based proposal system. So keep your eyes on the scientific merit when you write your proposals. And our call for proposal is open, and the deadline is in February. So I'm going to now stop sharing and take any questions people might have. Thanks for sitting through the half hour. Okay, I think
Slava has a question.
Okay, I'm sorry, it's very small. The available versus AIM capability described for FY27 is somewhat confusing. Can users propose experiments that would rely on the aimed capability for FY27, e.g. the 3 petawatt capability? Well, I think if you're planning your experiment, if it's not going to work at 2 petawatts, then it's probably not going to work at 3 petawatt either. But I think we'll certainly aim to push towards the 3 petawatts, but we cannot guarantee that. So that's why we have it as an aim. So I think 2 petawatts is reasonable to assume that could be available to you, but the 3 petawatts is still work in progress. So I think that's why we've got it as the aim. Should such proposals include backup plans in case the capability hasn't been demonstrated? Yeah, I mean, I would be surprised if there are many experiments that could be proposed for 3 petawatts that definitely couldn't do anything with 2 petawatts, but it's always a good idea to have a backup plan for. I'm sure experimentalists will agree with me. I'm going to stop the recording in case people wanted to ask questions that would not be recorded.